Yes. Okay, thank you. Good morning, good afternoon, good evening. I would like to introduce Dr. Bruno Girard, Director of the Sustainable Intensification Program at CIMMYT, who will give a welcome message for this seminar of today. Thank you so much. Dr. Bruno, you have the floor.
Yeah, thank you, Isabel. Hello, everyone. I hope that everyone is okay. It's a pleasure to welcome and briefly introduce Dr. João Vasco Silva, who joined CIMMYT not so long ago. I think you're probably the newest appointee of CIMMYT in terms of IRS. João joined CIMMYT 15 September. And João is from Portugal, but I believe he's becoming more and more Dutch because he's been in Wageningen for the last 10 years. So João did his graduate studies in Wageningen, and he did some research after his PhD also in Wageningen. His work is quite visible. I would say it's top-notch work because work with a leading group in terms of yield gap analysis. That's the group of Martin van Ittersum at Wageningen. And I think he's bringing to CIMMYT a lot of good skills that will complement already the analytical skills we have, not only at the program, but in the different programs of CIMMYT. João will be based in Zimbabwe very soon, we hope, when travel permits. And he will work directly with Frédéric in a series of projects. He might also link to other groups depending on his workload, but given his skills, I think he will be useful globally also and for some of our work, analytical work in other regions of the world, in Mexico, but also in Asia. So there is a growing importance. I mean, when I joined the program 9 years ago, we were more field agronomists than data agronomists. I think we can say data agronomists or data scientists, but more and more, I mean, to complement the empirical evidence we are collecting at the field or the landscape level, analytics is very important, and it's due to the diversity, heterogeneity, and the multi functions of the farming systems we are covering. So João will complement the team of crop and systems modelers, climatologists, remote sensing, econometricians, and spatial econometricians. And I think it's important for us to be strategic in our research for development work. I think part of our work is not only agronomic empirical evidences, but also creating knowledge and evidence to better guide development. So for me, the tools are only just tools, that's what matters is the tools you put together to answer critical and strategic questions. So João, welcome again. I think one more thing I want to add about João, I think we're sharing the same passion in winemaking. So that's something we'll probably have to talk about outside of this seminar. But João, welcome again, and really ready to listen to you and some interesting title, provocative, I would say, and we'll see what you have to say about it.
Good.
Yours.
Thank you very much, Bruno, for this nice introduction. Before I continue, I mean, can everybody see my screen and hear me well? Can you confirm, Bruno, if you can hear me and see my screen?
Yeah, let me just check because I have multiple windows open. Yes, I see your screen, Joe. I have also multiple windows, but I see your screen.
Okay, perfect. Well, thank you very much for this nice introduction. Before I start, I think it's a real pleasure to have this possibility to join CIMMYT, to join the Sustainable Intensification Program, and to have this opportunity to actually work worldwide with such a nice team of agricultural scientists. So, I mean, thank you very much for this nice possibility, and it's a real pleasure to be part of the team. So my talk for today is on promises and pitfalls of big data for agronomy. Towards decomposing yield gaps and benchmarking resource use efficiencies at local level. This is really then, or the focus of this talk is really the work I've done for my PhD thesis, but then the follow-up work that I managed to implement as part of a postdoc project, both that I conducted here in Wageningen. Is this working? How can I move the slide? Yeah. So Here, a brief outline for my talk. So just starting with a short introduction on the grand challenges that we have for the next century, on the sustainable intensification paradigm as a way to address those challenges, and then of course this big issue of this big data basically, and what can it bring new to agronomy and the way we do agronomy. This will be followed by an example of an application on decomposing yield gaps, where I will have to introduce some concepts and definitions that we developed and use to do so. And we'll provide also some evidence and some application to contrasting farming systems. This will be followed by then, a last section of the presentation from small to big data, where then really looking at thousands of farmers' fields data and in combination with some statistical methods and machine learning tools, then yeah, how can we assemble those? What can we learn from those? And to share some preliminary results on these. And then to finalize, just some take-home messages and some future plans also for me to be as being part of this team. So starting with the grand challenges that we left for the 21st century, I think the first one, and unquestionably, is to ensure food and nutrition security for all. I don't need to spare many words here, I believe, because we all know the population projections, and then the acknowledgement that we don't need to produce only calories, but also other foods. Second one, this needs to be ensured while avoiding land expansion and biodiversity loss, which of course are very much interconnected. I think just as a reminder, we live in the decade where land expansion has been the greatest for crops like maize and soybean, for instance. And then the last one, of course, is climate change adaptation and mitigation, because of course dealing with extreme events will affect all farmers and worldwide, basically. In some regions more than others, but anyways, it's a common ground there. Of course, this has been framed largely as part of the Sustainable Development Goals, as more of a policy initiative and a framework to take action, basically. And I think we all tend to agree with these three challenges that I'm mapping here. I think there is one fourth one that I want to highlight, is the diverging paradigms that we also live in agriculture these days. That basically, although we agree on the first 3 points, we tend to disagree on what should be produced where, by whom, and how. And I think in a way, this is also a challenge that we need to address. Well, one of these paradigms is, of course, sustainable intensification. I think the definition or the working definition I'm using here is basically narrowing yield gaps on existing land while increasing resource use efficiency. So to put it broadly, I mean, is to produce more with less inputs. But of course, there are some nuances here because, I mean, in itself, this is a contentious topic because, of course, it entails sustainability and intensification, and it's unclear to which extent and where can there be trade-offs between these two components. So I think it's very important that our research makes that explicit. As a second step, of course, I mean, scale matters very much because if we talk at sustainable intensification at field level, we might be talking about technologies. If we talk at regional level, we might talk about prioritization, where should this be targeted based on, for instance, existing yield gaps. And of course, I think when you talk about the farm level is also when things get a bit more blurry, but I think it's actually very much needed work there towards understanding, well, how sustainable is actually sustainable intensification for farmers and at farm level, given their knowledge, opportunities, constraints, and so on. The next step is, well, recently there has been a review paper by 2 American colleagues really calling for a research agenda and prioritization of research agenda on sustainable intensification for staple crops, really putting or bringing to the table the importance and well, how ahead is this paradigm towards solving the challenges for the main bread baskets worldwide. And then as part of this research agenda, I think there is this big hope for big data from farmers. And I think, yeah, this big hope comes very much related to the perspective to deliver agronomic yield gains and environmental standards at scale. Because of course, then if we can absorb all these farmer data with all and link it up with all sorts of other information, I think, yeah, there is a very big hope that this can be used for the good of the sector and for the agricultural sector and for rural communities also in developing countries. So on big data, this is I mean, is it the end of traditional agronomy? I mean, I think this question, I'm not the first one to ask it, but I think, well, it might deserve some reflection, because I think the types of information we are dealing with do require new ways of doing things. Although I believe that the solid agronomic knowledge and the solid agronomic theory might not be completely, or we should definitely not give that up completely. So when I talk about big data, my working definition here is a high volume, velocity, and variety of information to require specific analytical and technological methods for its transformation into value. So I think it's really about three core words here: information, so data itself; methods, so how can we process those data; and transforming into value. So this issue of value, that is the added value that we are bringing it with these new methods and with these data that we are bringing in, the additional value that we bring with it. I think there are many opportunities here, as I briefly mentioned earlier. I think, well, we all perhaps, I'm not into this research for long enough to see changes or to really experience many changes over time. But I believe that we do see, perhaps everybody has a bit that feeling, that we have increasingly amounts of information. I mean, that's certainly true in the developed countries, where farmers are increasingly collecting more and more information and measuring all sorts of things. And I believe also in the developing countries that is the case, given the easiness and the cost effectiveness of these days to collect large amounts of information. In addition to that, of course, we have increasingly available spatially explicit databases with weather, soil information, socioeconomic data, and so forth. And of course, linking these two aspects, so this farmer field data with all this spatially explicit biophysical and socioeconomic data, really gives new opportunities. And I think the opportunities that I think are clearer are these two last bullet points then expressed here. One is that by working with all this farm data and being in a special explicit way, this can be considered equivalent to run hundreds of trials to evaluate multiple management by environment interactions in a very cost-effective way, or at least much more than if we would have to conduct all those trials in situ. And the second point is, of course, it really allows us to develop benchmarks for key metrics and indicators on resource use efficiency and environmental quality that can guide, well, our research and development activities, but also stakeholders and policy towards measuring, okay, are we making the desirable progress or not? And to evaluate whether the interventions that we are having are actually useful and practical. But of course, there are challenges. And I think I mentioned here three challenges that to me are very key. One is that data quality. I mean, we all know that how complicated it is to actually conduct surveys, to conduct trials, to ensure that everything goes right from beginning to the end. And I think this is especially critical because it needs to be done without, for us, simplifying farmers' reality. So if we need we might be looking for information for one crop, but of course, important to mention or to consider that farmers might need to manage animals or other crops and might have other sources of income. So all these issues, the more we need, the more complicated it will be to ensure quality of the overall information we are gathering. The second point, I think, is that many of this information is currently very scattered. So in the laptops of different colleagues, or in different dataverses, or in different websites, you name it. So although it's available, it's very scattered and we need considerable time to actually harmonize it and to make it usable. And in addition to that, I think there are many ownership and privacy issues that also sort of constrain the use of this information, because, I mean, who owns the data? Is it the researcher? Is it the farmer? Is it the co-product? I mean, all these, the legal frameworks around all these about all these type of information, I think is still developing and yeah, poses some challenges, because of course we can also use this information against farmers, which is not really our intention. But of course, people might be reluctant to share this even if for research purposes. And the last one, I think, is a bit more on training. I really think that agronomists, then to handle these piles of information and to add value to it, I think we really need to master many different algorithms, many different tools, which can be challenging. I mean, because from crop modeling to different statistical analysis to perhaps a bit of econometrics to some basic principles for data cleaning. I mean, you name it. It's just skills that, I mean, many of us were not taught in our undergrad. So my research focuses up to now on four mainstreams, as highlighted in this slide. The first one on decomposing and explaining yield gaps at systems level. The second one on benchmarking resource use efficiencies at the field level, mostly focused in Northwest Europe here. A third one on crop model parameterization, improvement and application. And then the last one really on big data analysis for contrasting farming systems that, yeah, I will present later. And well, my workflow is mostly built upon Python, R, and of course field experience to really give context and to make sure that all the analytics that we develop and that we do are meaningful and are contextualized and actually can add value to the regions where we work. So in my talk, I will basically focus on the first then and on the last point due to time constraints, but I'm happy to have any further clarification questions about the other two as well. So starting with the yield gaps, I think is important to introduce as a first step what we call in Wageningen the concepts of production ecology. We start by defining the potential yield as a set of defining factors, being mostly environmental and genetic. So CO2 concentration in the atmosphere, radiation, temperature, and the genetics. And of course, we can manipulate this potential yield through breeding. So that's sort of the main way that we have to manipulate this yield level. As a next step, we identify the limited yields. So in this case, the water or the nutrient limited yields. And we do so by adding here, by heading to the defining factors, the so-called limiting factors on water and nutrients. Of course, we can raise these limited yields towards the potential yields through yield increasing measures, such as providing irrigation water or adding nutrients independently of the sources. As a next step, or as a last yield level, we have the actual yields. And these are really what we observe in farmers' fields. For this yield level, we further take into account then the contribution or the yield reductions from weeds, pests, diseases, and pollutants, such as, for instance, soil acidity. Of course, we can increase the actual yield towards the limited and the potential yield level by alleviating these factors through crop rotations, crop protectant agents, I mean, you name it. And then as a last step, the difference then between these potential or limited yields and the actual yields is what we call the yield gap. As a next step, I just want, these yield gaps, they have been mapped worldwide as part of the Global Yield Gap Atlas project. And I just want to give you an overview then of what is available for core CIMMYT research areas. Starting, for example, with irrigated wheat in Mexico. We see here the main irrigated wheat areas in the country. And we see, in green, that farmers realize about 50 to 70% about the potential yield that they could achieve with optimal management. The situation is quite different in South Asia, where, well, for rain-fed wheat in this case, where yield gaps are, where the actual yields or where farmers reach only 10 to 30% of their water-limited yields. And a similar picture is, can be or is shown here for 5 countries or 6 countries in Eastern Africa for rain-fed maize. So clearly, especially looking into rain-fed wheat in South Asia and rain-fed maize, it's very clear that there is plenty of opportunity to narrow these gaps, although we need to understand a bit better actually how to do so. And that's basically where most of my work comes from, is really to develop understanding and explanations for the causes of these gaps. So to do so now, to introduce you to that concept, I think it's important to think a bit conceptually, so that I can guide you a little bit to the concepts and definitions that we developed. And to do so, then, is important here to take this example, to have the yield level in the y-axis here, and then to have input use, and this can be multiple inputs. So think of fertilizers, water, weeding, labor, you name it, in the x-axis. So basically setting up a relationship between inputs and outputs. If we make a survey, then these are sort of the variation that we observe for individual fields. So for example, for this field, this would be the amount of input use, and this would be the yield level obtained. So these yield levels is what we call the actual yields. Now, the first step in this analysis towards disentangling these yield gaps is to identify the best performing units for a given input level. And we do so using using frontier analysis, so some econometric methodologies here, to really identify then what we call these technical efficient yields, which can be defined as the maximum yield that we can reach for a given amount of input use. Now, in this case, we can see that these two fields, so depicted here by these 2 gray dots, one here and another one here, although they use the same amount of inputs, they get very different yield levels. And this difference then is what we call an efficiency yield gap. And this can be explained by suboptimal time, space, or form of the input supplied. So not by the amount, but by other components of crop management. As a next step, we compare these technical efficient yields to these highest, what we call these highest farmers yields. So an example of that would be the top 10 percentile of the actual yields in the sample. And we use then these highest farmers yields to benchmark our individual technical efficient yields. And then the difference between both is what we call a resource gap. And actually narrowing this gap requires increasing amounts of input. So really requires moving along the x-axis to realize the additional yield that we need to reach these highest farmers yields. Now, this situation shows you or provides you an overview of the best technologies available on farm, but still I think it's important to benchmark those against the potential and the water limited yields that I showed you earlier. And that is basically what this dashed line, this future frontier or this other frontier sort of depicts. So it's sort of how far are current farm technologies from agronomic best practices. And then this difference between water limited and highest farmers yields is what we call the technology yield gap. Before I continue, I think it's just important to highlight here that this only makes sense, of course, if we control for biophysical conditions. So to make sure that that all differences between fields can be attributable to management, but not to soils or weather. So I think that's an important remark here. Now, towards an application, I've been lucky to be able to apply these concepts in a standard way in two very contrasting case studies that I will introduce now. The first one was on mixed farming in southern Ethiopia. This was a collaboration with Frédéric Baudron when he was based in Ethiopia back then, and as part of the Fakazi project. So here we analyzed 200 farms for the year 2012, and we analyzed, or we did this yield gap decomposition in depth for maize in Awassa, a site in the lowland area of the Rift Valley, and for wheat in the highlands in Asela, in a wheat-based system. I was also lucky enough to visit the Philippines and to visit Central Luzon in particular, where rice is a very important crop. So this was the second case study that I could build upon. And here we really made use of a very long-term survey starting in 1966 up to these days actually, where the same farmers have been interviewed every 4 to 5 years. And here the crops of interest are then a wet season rice crop. And then finally, in the place where I'm now here in the Netherlands, I was able to also set up a case study on arable farming, where well, we could gather detailed information on 175 farms over a period of 5 years or so, and we could do a detailed yield gap decompositions for wheat, barley, different types of potatoes, sugar beets, and onion. So how do the results look like? This figure is intended to summarize the results of all yield gaps, and I will guide you through it now. So here, each bar represents or depicts one crop in one country, starting with maize in Ethiopia, wheat in Ethiopia, wet season rice in the Philippines, dry season rice in the Philippines, and then barley and wheat in the Netherlands. And then the y-axis, I'm showing the yield gap closure. So basically, I'm expressing the actual yield and the different yield gaps as a well, in proportion to or in relation to the benchmark, to the yield ceiling, either the potential or the water limited yield. Then the dark colors here represent the actual yields, so or the relative yield gap closure. In well, the bars right above represent then the efficiency yield gap. The right above ones represent then the resource yield gap, and the light colored bars on top then represent the technology yield gap. So what can we conclude from this work? In a first step, that, well, perhaps this is not new to any of you, that yield gaps are about 25%, or sorry, actual yields are about 25% of the water limited yield in southern Ethiopia. So there is a very large yield gap in these farming systems. And we see that, well, the technology yield gap here on top really explains 50 to 55% of the yield gap. But then, well, narrowing efficiency and closing and resource yield gaps, so current technologies have the potential to actually double actual yields for both wheat and maize, which of course I think is very good news also for this region. In case of rice in the Philippines, we see that well, farmers reach about 50 to 55% of their potential yield. And here we do see that the yield gap is explained by a combination of the three intermediate gaps. So there is scope to improve yields by narrowing efficiency gaps, by improving the agronomy, the time, space, and form of input use. There is also scope to improve well, to narrow yield gaps by increasing slightly the amounts of inputs of the inputs applied by some farmers or in some farmers' fields. And then lastly, the technology yield gap comes to some better management of some water constraints that still prevail. As a last step, in the Netherlands, we see that, well, yield gaps are smallest, and farmers manage to reach around 70% of their potential yield. And we see here, I mean, resource yield gaps, so these two tiny bars, are very small. So because, of course, farmers are using way too many inputs. And most of the yield gap is explained here by the efficiency gap, meaning that fine-tuning current practices is really the only way forward towards productivity increases in this farming system. I mean, technology gaps might look a bit too large in this farming system, but they capture some water limitations that farmers cannot really handle themselves. So it's questionable whether this can be narrowed further. I think now it's important to show you a bit of the variation of the data that we are working with. And here I have to make use of agronomist's most favorite plot, perhaps, and that is the plot showing yield response to nitrogen. So here in the y-axis, you have cereal yields. In the x-axis, you have plant available nitrogen applied. If you have these two variables, then you expect a curve like this with diminishing returns to nitrogen applications. Now, if we plot data from farmers' fields in Ethiopia, we see they are all, or their yields for maize and wheat are all below 3 tons per hectare, and nitrogen use is well below 75 kilograms nitrogen per hectare for most fields. If you look into farms in the Philippines, we see that productivity for rice ranges between 2 and 6 tons per hectare, and then nitrogen applications range between 50 and slightly or 150 kilograms nitrogen per hectare. So much more intensive system than we have currently in southern Ethiopia. And then finally, if you look into barley and wheat in the Netherlands, so barley is light blue and wheat is then the dark blue. You really see in the case of wheat that yields are plateaued at around 7 to 8 tons per hectare, and that nitrogen applications are for most fields actually above 150 kilograms nitrogen per hectare. And yeah, above this threshold, we basically don't see responses to more nitrogen applied in farmers' fields. Now, if we use this data to basically capture a gradient between sustainability and intensification, I think we can conclude that, well, in Ethiopia and perhaps most of sub-Saharan Africa, it's justified to focus on more with more, so more output with more input. If we focus, or if we look into what data tells us from the Netherlands, I think it's very much adequate to propose a strategy that focus on producing the same with less inputs. So to really, maintain same yield levels and improve resource use efficiencies by decreasing the amount of inputs applied. And then if we look for rice in the Philippines, I think sustainable intensification might really be the most adequate one, meaning that we should really target to have more output with less input. At least for many farms, there is a large scope to actually achieve that. Now, just briefly, I want to guide you through other examples of this framework that I have applied, that I have used. Well, I hope you are still with me. Yeah, okay.
Yes, we are.
Okay, good, thank you. Because yeah, just talking to a screen, it can be a bit challenging at times. And these other examples then, I will start, or I will focus mostly in the context of the work we have done in developing countries then. So I was lucky to be able to expand the work we have done with wheat and maize in Ethiopia, also in collaboration with colleagues in CIMMYT, namely, well, Kindi Tesfaye, Muti Jaleta, and Jordan Chamberlain, and with Frederick as well, of course, to really expand this work to the national scale and start using national representative data sets to really map out how these yield gaps look like and what are opportunities to narrow them. Overall, I must say the conclusions are very much, well, they are summarizing these 2 bullet points, but they are very much in line with what I mentioned earlier. So, I mean, the large contributor to the yield gap is this technology yield gap. So meaning that the input use in the highest yielding fields is still way below what would be needed to actually reach these water limited yields. So that would be the first key lesson, number 1. And the second one is that, well, even though that is input use needs to be increased a lot to reach these yield ceilings, there is a large potential to actually increase productivities by focusing on current technologies and within the current means that we observe in our sample of farmers. And that by fine-tuning current practices, we can actually double current yields. And funny enough, this is basically roughly what has been estimated as the requirement to reach self-sufficiency for maize and wheat at national level in a country like Ethiopia. So, I mean, although these yield gaps might look small, I think their implications and their contribution is actually quite, or can be quite large. Another point just to highlight, the framework has been expanded also for economic and policy analysis by other colleagues in my previous team. I've worked together with Frederick to also map these yield gaps for wheat farming systems in the Rwandan islands. Very similar situation, I would say, to what we found in Ethiopia. And I'm currently working with colleagues in IRI to actually expand then the yield gap analysis that I've done for the Philippines to other major rice bowls in Southeast Asia. So we can really also try to understand how these yield gaps play out in different regions or in different countries in the region, or in different rice bowls in the region. I think this is particularly important there due to the past very different historical developments between different countries in this region of the world. So this is basically the first part of my talk. I think it's covered up to here on the yield gaps, and then I will move on towards sharing some early experiences that I had with processing this big data, and then the challenges that I also faced in doing so. So now, as I said, moving from small to big data, and this is work that, I mean, it's preliminary work that is basically in preparation. But I'm showing you here just for your references regarding the variability that we have in these national representative data sets. On top for wheat yields and nitrogen applications in Ethiopia. And then in the bottom, basically the same, but for maize, also in Ethiopia. So huge variation. I guess if you are used to work in experimental stations, perhaps you would have straight lines and very neat lines for this relationship. But well, this is sort of the variation that this type of data brings us, and that we sort of have to deal with in the analysis that we are currently doing. Then this is how this looks then for the Philippines. So similar relationships, but in this case for rice. On top in Nueva Ecija, the key rice producing area in the country, and then for other regions around it in the plains of Central Luzon. And then finally, you see then the relationships then for winter wheat in the Netherlands and for barley in the Netherlands. So anyways, this is just to show a bit of the variation we have to deal with, and to say that, of course, I mean, by pulling these analyses and this data together, I basically arrived at the point that we had more than 10,000 field year combinations, well, from different regions and so on, but all for cereal crops, all relatively recent data. And of course, this provides a great basis to really start investigating, okay, I mean, how can we use this information? How can we mine it? And what can we actually learn from it? So this made us ask a question, which is framed here. And basically, it is as follows. With which accuracy and precision can we actually predict crop yields in time and space using these thousands of observations that we have? I mean, how good can we predict then yields in other regions, in other years, or for different farms? So to tackle this question, we developed a sort of, a master student in the group developed a sort of an analytical framework for this, which start with basically describing the yield variability with a set of box plots, scatter plots, so really descriptive analysis. It moves on to the quantification of that variation. So what is the proportion of the variance that can be explained by the farm random effect, by the district random effect, or by the region random effect? So where is most of the variation in the data coming from? It follows then by a box on explaining that yield variability. So throwing in or linking basically the yields, the cereal yields that we have for these fields, together with a set of biophysical information and agronomic practices that we also have for those fields. And this can range from, well, aridity index, temperature, seasonality, growing degrees day, nutrient management, weeding, labor. I mean, all sorts of information that we could retrieve both on the biophysical characterization of the fields and on the management of those fields when it comes to the agronomy. So to really try to explain the variability behind the data that we have. And then finally, we do some prediction exercises with some model cross-validations with data resampling in space and time. So this is really about, I mean, I mentioned already variance components and so on, but we use here then mixed models and also a machine learning algorithm like random forest. So that's what has been tested here. Well, and now I think this is my last slide with content. I will just show you some preliminary results. Well, they are in this table. Sorry if it's a bit overwhelming here, but here I'm just showing you the R-square, so the correlation coefficient here between the predicted and the observed yields. Just to give you an overview then of the proportion of variation that we can explain, and how does that differ then for different crops in different farming systems. We've also done this for the root mean square of error and for the modeling efficiency, which are of course much better indicators for accuracy and precision of these models or of this type of tools. But I will stick to the R-square here because I think they illustrate the point and perhaps might be of easier interpretation. So here we have then well, 6 columns, one for each crop in the different countries. And then you see then 2 sets of results, one for linear mixed models, and then one on the bottom for random forests. The first line of each of them, highlighted here, refers basically to the full model. So what is the R-square of the full model? And here I mean of using the entire data to feed, to fit and to get a relationship between inputs and outputs. So we can see here that basically based on all the information we have, we can explain up to 30% of the variability for smallholders actually with the data from smallholders using here the mixed models. We can explain up to 35% then with random forests. In the Netherlands, the picture looks a bit better, especially for winter wheat, where we go to 40% and to 60%. Now, this is actually done with a full data set and with all sort of variables included. So you can imagine that there is some overfitting here. And even with that, with the overfitting, with all the sort of variables included, we don't go beyond, especially in Ethiopia and Philippines, well, 25 to 30% of explained variability, which in my view, I was a bit disappointed. Perhaps I was too naive, but I was a bit disappointed with these findings. Now, when we start doing cross-validations across zones, farms, and years, and what I mean with this, I mean that we use some zones or some farms or some years to train our models and to get to make them learn from that subset of data, and then we apply those relationships that have been learned within the training set to a testing set that is then independent, and that independent that covers then independent zones, independent farms, or independent years. And I don't want to elaborate too much on details here, but we see that as soon as we start doing these cross validations, actually the statistical performance of our models, I mean, collapse enormously. Just look, for example, here the case of wheat in the Netherlands, that basically making predictions from one year to another year. I mean, we basically stop explaining any of the variation in the data in this testing set. So of course, I think these are challenges that come, or what can explain these basically. Perhaps data quality can be an issue, but also the agronomy itself and the environments where we have to work with that. The timing matters, each year is a different year, there are many interactions at stake. So, and all these either require piles of information that we don't have. And if that's the case, then, well, using or building upon farmers' field data for this type of analysis might be a bit of a futile exercise maybe, and better we rely then on mechanistic tools such as crop models then to make such assessments. But of course, those also come with specific costs in terms of representing reality and of flexibility, and also because these tools are data hungry when it comes to their parameterization. So I will finalize now just with some take-home messages. The first one, very briefly, well, sustainable intensification has different meanings in different farming systems and provides different opportunities at local level. I believe the 3 contrasting case studies I showed illustrate this point. The second one, to note that most of the yield gaps in Africa are mostly attributed to technology yield gaps, but still, I mean, really looking at current technologies and improving the agronomy of those current technologies can have a great benefit in these contexts, because they can basically contribute to double current yields. And as I mentioned, in the case of Ethiopia, deliver the production needed to, well, for self-sufficiency at national scale. And then the last one on big data, I would argue, and also based on other experiences that I haven't presented here, that big data are generally useful to describe cropping systems at regional scale and to derive benchmarks for farm performance, so to set up upper bounds of performance, of productivity, of resources efficiency, but they are not as good or not as suitable to predict and explain yield variability in time and space. Of course, when we want to use this type of data then for technology targeting and things of the like, I think this is something we have to bear in mind, that I mean, we need to understand perhaps better the algorithms we do, but also to collect better type of data and to perhaps also be down to earth towards the expectations that we can build from what we can get from this data. And then to finish off with my last slide in terms of future research and also what I would like to engage on and to collaborate with you now within my new position in CIMMYT. I think the first one is really on assembling databases and methods for doing agronomy at scale. I think these are part of projects that I believe are coming up in Africa, especially in the region, where there is opportunities to actually gather this information and work on workflows to really, to really guide interventions and to really start implementing a little bit this concept of agronomy at scale. I think here it really touches upon getting data, harmonizing data, and making it usable and available for biophysical and socioeconomic information, and then on using those and develop methodology, testing methodology for elucidating on returns on investment, on technology targeting, and on sampling frames, for example. These are just 3 examples that come to my mind that can be suitable applications here. The second one, I think, as I showed earlier, I think is really to decompose maize and wheat yield gaps in CIMMYT's research sites. I really think this is a low-hanging fruit because we can really capitalize on existing data sets. And I think this could really provide a very nice global picture for the main smallholder regions, actually, where these crops are produced. And I think, although, I think this would be really, I would be certainly very, very interested in supervising and collaborating and helping whoever is willing to and is interested also and can take the time to help in setting up these analyses. And another thing here that I think is good also to prioritize is to establish data collection tools and workflows that can really speed up this type of analysis. I think this is something really that I think I can contribute also in relation to the first point. And then the last one, and well, my apologies if I'm being over ambitious here, but I think I'm just taking the chance to just draw some ideas on the table and then to see whether that's possible or not. I think time will tell. But the third one would be really on benchmarking maize and wheat resources efficiencies, also in these smallholder systems. And I think there is a lot of things that we can do here in terms of really data-driven analysis with agronomy on-farm trials, for instance, that have been collected across many different regions in the different continents even. But also of breeding data, because I think these are very useful for simple crop ecological relationships that we can derive. And I think they are very useful then in the context of crop modeling, really to crop model improvement, crop model parameterization. I think we are always crying, at least I talk from my previous position in Wageningen, we are always crying for good data sets that we can actually use to challenge our models, to test them, to crash them, and to basically improve them. I would leave it here, but before that, just a word of thanks to my former supervisors and collaborators, of course, in most of the work that I've presented here. So starting with Professor Martin van Ieterszoon, Dr. Patrick Reitsma, and Professor Ken Giller here in Wageningen. In IRI, I was lucky to work with Alice Laborde, head of the GIS lab these days. And then with CIMMYT, in addition to the names I mentioned earlier, I think Frederick was also a very good colleague and collaborator in setting up these analyses and also contributing to the storyline that I also just presented. So I would like to leave it here, and I'm very, very happy to take any clarification question or any advice, any remark that you may have. So thank you for your attention.
Thanks a lot, João, for that very interesting and clear presentation. I think we have about 15 minutes for questions. And I'll take the advantage of sharing this session to ask the first question. I mean, you've been working on yield gap analysis on single crops. And in fact, most farming systems we cover are multi-commodity, and the decision making is usually at the, in terms of resource allocation, is at the farm level. So a yield gap might be something that's, you know, intended by farmers, because if you look at crop livestock systems, for example, they have a better return on investment on you know, putting inputs, either labor or feed on livestock than on crops. So what's the state of research? I mean, is the yield gap a good entry point for that type of research, or what's the state of research looking more at productivity gap at the farm level than the, you know, strict yield gap, which is a good indicator, in fact, for the intensification potential, of course, as you show in your presentation.
Yeah, well, that's a very nice question. Thank you for that. Well, I think, yeah, how can I say, the way the approach, or how can I put, I think when we pool then different crops let me take one step further. I do agree that the farm level is the key level where decisions are taken, and that those decisions have a key influence on the yield gaps that we observed for the individual activities of the farm. So all these efficiency gaps, for instance, in the case of Ethiopia, where we have actually, well, we have the cereals, but you have legumes and you have, well, livestock as well. I think that's a clear example. We really did a detailed analysis on labor and really tried to understand, okay, to which extent is, if I use too much labor for one of my crops, do I have to compromise then the labor that I'm using for my other crops? And to which, and then what is the yield gap or the productivity loss that you have by yeah, with the type of decision that you take. So at least that's a bit the way I have nuanced this farm level perspective in this yield gap work. So to keep the crop focus, because I think we can relate easiest to that level, to that crop level. But then, of course, give the context, give the nuance, and bring in those decisions to explain what happens at individual crops. I have to say that, I mean, the results are not always clear, and I think we all tend to agree that these decisions and these interactions are very important, but it's very hard to put that in a one-to-one relationship with the R-square of 90%. It's really hard with these data sets to actually get these relationships crystal clear. So I think, yeah, we need to do a bit more work there. Another example that I can give you is an application I've done particularly for the Netherlands, well, and to some extent for the farms in Ethiopia as well. Is to basically to start pooling all crops at the farm level, and for that we use economic indicators or nitrogen indicators, for example, or labor indicators. Anyways, we need to use another metric that allow us to do that pooling of the different crops of a farm, and then to start comparing farm performance based on those farm level performance indicators. So this has been addressed in addition to this crop level analysis in the publications that were cited. And I should also say that I have a paper in preparation now where I hope to nuance that a bit further. So to really ask, okay, what is the, economically speaking, then how interesting that is for sustainable intensification for the farms, or what are the labor implications, or, you know, when you look into nitrogen use efficiency and nitrogen surplus, then how does that link? Are there synergies or are there trade-offs there? So yeah, I hope that answers the question, but yeah, I mean, point well taken.
I mean, it will be interesting to have your addition to the group, because we are looking a lot at, you know, trade-off and synergies at the farm and a bit less at the landscape level. But I mean, that's all those things combined are more powerful than, you know, an individual approach or line to look at farming systems potential solution innovations for those systems. So good. So now we'll start taking questions. If you can ask, João is new in CIMMYT. When you ask a question, if you can introduce yourself, would be nice. I'm looking at little hands now. I mean, if you can raise your hand if you have a question. And Isabel, you can screen with me. I guess if you raise a hand, it will come on top, no? Don't tell me you don't have any question. I don't believe that.
But there are interesting ones in the chat box already, Bruno.
But we're not able to do anything.
Okay. But if you put the thing in the chat box, raise your hand, and then we'll collect also the questions we will not be able to ask now, and then we'll send it to João. Isabel is doing that, I think, very well. So if you have a question in the chat box, raise your hand like that. You can use your voice. I mean, those webinars sometimes are killing people not talking, because just one or two people talking. So if you want to talk, raising.
Bruno, Sam here. I'm not able to raise my hand or type in the chat box.
Okay,
But
then
can I jump in for a question?
Yes.
Okay. João, thank you. Really nice presentation. Just had a couple of quick questions. One of them is like, what is the threshold for big data? For example, if you're looking in the trials, agronomic trials, are we looking at 100 farms, 1,000, 10,000? You know, where's the threshold? That's one of the first one of the questions. The other is, this appears, a lot of it appears to be ex post. Now, if you wanted to do an ex ante approach to this, now how do you set up a set of agronomy trials suited for big data or for agronomy to scale?
Yeah. Well, thanks, Sam. Very nice questions. I think the first one has an easier answer than the second one, perhaps. But yes, I think this is my definition here, as I'm sharing now in the screen, really of big data. And I think this comes from some library research, and I think there is no really number for that. And I think, as I mentioned, there are two components here: is the amount itself, but I think perhaps even more than the amount is the methods that you need to process those data. And perhaps, I mean, everything that is big enough, then you can handle in Excel file that you can keep track of all the calculations and keep track of all the additions and so on that you do. Perhaps then, yeah, if you need a script-based language, which I think that should be the for the future, we cannot really live without it. I think then perhaps we start talking about some sort of big data there, because then the possibilities to link that information with other information just explodes. I mean, just there is some exponential increase there in what you can actually do. So yeah, and in short, then I think, yeah, the methods are as important as the data, and I would refrain then to coin it with with a specific number of, okay, this is 10 trials or 10,000 trials. I think that's I would refrain to do so. The second step, I agree very much that this is exposed, not really ex ante. But on the other end, I mean, I think this can also be used for ex ante prioritization, right? Because if you look into the yield gap framework that I've used, I mean, at least now I think we can really, at least focusing on these efficiency gaps. And if I would have to go and do a questionnaire to farmers, I think perhaps I would not use, or I would not focus so much on some capital information, or some other issues that might be a bit on the side. But I would make sure I can get the key information that can help me to really dive into this efficiency yield gap. So I mean, when are you doing your sowing? When are you harvesting your crop? When are you applying your fertilizers, if you do? When are you doing your weeding? So I think or looking at rainfall patterns over time for each individual field. So I think these would be really something that by saying, okay, these efficiency gaps are actually what matter, that then what I would take from these to actually prioritize future interventions or future research, basically, in the field. Of course, I haven't done that to this point, so this is only talking. But anyways, I think this would be something really that would be very interesting for me to also engage with, and to also learn from other colleagues that have more experience, of course, than me on these. I don't know if this answers your questions, but I think that's as much as I can say.
No, thank you, and we'll follow up, because this is an interesting topic. Yeah.
Yeah,
thanks,
João. The next question, I went to the chat box, always follow instructions from Frederick. And Gokul has a question, so if you can take the mic, briefly introduce yourself. Gokul?
Yes, thank you, Bruno. My name is Gokul Pordel. I've been working here in CIMMYT, South Asia, in the project CISA since a long time, and I'm also working with this machine learning stops. So I have a thank you, very nice presentation. I have a couple of questions. When you presented all this linear mixed model and random forest results, the Rsquare, it seems like on an average overall, with exception in Netherlands, that's about around 60%, but in other regions that was less than 50%. So perhaps what features that you have included in the model, because random forest or any type of model is sensitive to the features, right? So can you say, what are the features that you included in the model? First question. Second question was that generating those the maximum yield potential and the yield gap analysis? Did you simulate either by dynamic crop simulation models or whatever you have used, the or limited or the yield potential level? Did you simulate all the farms or just a single sort of simulation? Thank you. These are two of my questions.
Yeah, very good questions. Well, thank you for those. I mean, I can provide you a more extensive list of the variables used here, but I mean, we just used to go to the point. Then the climate zonation of the global yield gap atlas, which includes 3 biophysical components here. So growing degree day, temperature seasonality, and aridity index. We used a set of soil data, also as used in the global yield gap atlas. So the depth of the rooting zone. I think perhaps that was the only one. And then we used all other data comes basically from recorded by the farmers. And it includes, well, nitrogen application, seed rates, labor use for weeding, number of plowings. Well, what else comes to my mind? Soil fertility, other stresses that farmers reported. So all the amounts that have been reported in the end of the season. So I mean, I can give you the full extensive list of data there, but anyways, it's important to mention that is all the sort of agronomic variables that comes in these standard questionnaires that have been done to farmers, or information that farmers have to record basically for their in the case of the Netherlands, for their crop registration and for their bookkeeping basically. But anyways, I'm happy to share a list of variables there. And of course, we are missing here, I know, I mean, a lot of the information is regarding to when are the applications done, which type of nitrogen is used, or of weeding was used. And so many of these, time, space, and form variables are missing from this analysis. So that might explain a bit, perhaps, these low R-squares. Regarding the crop simulation modeling, what we do here, or at least what I did for my application in the Philippines, I basically just run the model for different varieties that I retrieved from that were representative for the varieties cultivated by the farmers, and I just run a sensitivity analysis basically with the model. So to basically compute nitrogen response curves to illustrate basically this technology yield gap, and to just basically compute this curve that sets you your agronomic best practice boundary that reaches the potential yield. So there is this 2017 paper in the European Journal of Agronomy that provides an example of that. For the other case studies, I've built directly upon the global yield gap atlas, for which, well, we take the cropping system as a reference and the best farmers as a reference, and then we use those to parameterize the models and to run the models, and then to give one value per year per crop per region. So all this is spatially explicit, that we can then link up with the actual yields that are coming up from the individual farmers' fields. So I hope this answers the questions.
Yep. Thank you. One more question on the follow-up. Just when you say that you use you integrated different data sources, either from remote sensing or the crop management or maybe socioeconomics. So did you face the collinearity problem while checking the correlation?
Yeah, sure. I mean, all these things need to be assessed, of course. I mean, I refrain from going to the socioeconomics. My approach is always to say, I'm interested in explaining yield variability, and for me, what is the first driver of that is the biophysics and is the agronomy. The socioeconomics might explain, but to me, they are more of a driver of your crop management and of the agronomy that we use than really of a productivity. Because I mean, okay, you can have more capital, but your crop doesn't really respond to capital. It responds to the fertilizer that you are putting. So that's a bit sort of the approach I always follow in this type of analysis, which of course can have limitations, but at least that's my way to structure this.
Okay.
Thank you.
Time is up, but I mean, I don't have a meeting after this one. So for people, and I will check with Isabel because she's the one organizing. Can we stay 5-10 more minutes, Isabel, if there are more questions? I see 2 questions in the chat box. So
yes.
João, there were 56 people attending, and some people already left because usually they start all the meeting by the hour. I see a couple of questions. Rabe, you have a question and a comment, I think, isn't it?
Yeah, thank you, Bruno, and thank you, Joe. It was quite interesting. And you said that you found in your research that technology gap was the major contributor to the overall yield gap. most importantly in Africa, I mean, so in Ethiopia. And my question to you, would you please elaborate more about the decomposition of which technology contributes for how much yield gap?
Yeah, that's a very good point, Rabe. Thank you for raising it. I think we struggle, and I think you are touching here upon a critical aspect of this framework, I must say. And I need to use this framework basically to explain it, or this figure to basically explain you that. I think in particular case of what we have seen in Ethiopia, many of or a lot of that yield gap is actually explained by inputs, by suboptimal use of inputs. And why is that? I mean, how can that not be part of the resource gap here? And the reason is that, so the highest farmers yields in Ethiopia would be somewhere over here. So basically, the resource, if that would be the case, then the resource gap, I don't know if you can see my screen here, if you can follow.
Yes.
But then my resource gap would be the difference between this individual point and this point here, right? But all the extra inputs that I would require to actually go all the way to the water limited yield would be captured by the technology yield gap. So this is sort of an artifact here that, well, you know, it doesn't really help to make this analysis in these low input settings, because yes, all the input that is, or how can I put it? If the highest farmers fields use much lower amount of inputs than what is required for the water limited yields, then according to these definitions and to this way this decomposition works, then those input limitations or those suboptimal amounts of input would fall in your technology gap, not in your resource gap. So, and we have done that actually for Ethiopia, and then we can see that only by increasing inputs to the level needed for the water limited yield, then we can narrow basically the yield gap up to 70 to 80%, which is often, I mean, what is sort of pointed as an attainable yield level that we can reach. The other 20% would come again, I mean, fine tuning some practices. I mean, mechanization can help there. Optimizing the use of water to avoid water stress in the season or not. So all these other small things can then help you in the last 20% bit towards the productivity gains. I think that's a bit in short, and sorry for being conceptual here, but I think in short, that's what is behind these large technology yield gaps, particularly in Africa.
Thank you. The next question is from one of your former donor, Victor Comrel, who is the manager of the both maize and wheat CRP. So Victor, you have more conceptual questions on big data. Victor, I can see you.
Sorry, it's not really. Yeah, I suppose it's a question, but no. When I heard this, another colleague's question about thousands or hundreds of thousands of farms, I thought that the big data opportunity is more about that you can have higher frequency of observations over time, and that you can look at different kinds of observations also, and that you can link them. I thought that was the big thing about big data, not so much if it's 100 farms or 1,000 farms.
Yeah, I would agree very much with that point, of course. I think, yeah, we can collect information in a much faster way, and then we can basically, as long as that is especially explicit, we can basically link it up to any other sources that are available, basically. So yeah, point well taken.
Okay, I don't have any questions in the chat box anymore. So if you can either take the mic or raise your hand and take the mic. Yes, Mahesh.
Thank you, Joe. It's very nice presentations. Just I'm looking at how we look, further that to combine.
Introduce yourself. Where you?
Oh,
work.
sorry. 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 So myself is Mahesh. I am based in system agronomist, based in Bangladesh. Can I ask now?
Yes, of course, Mahesh. I was just at the João.
So I'm looking very nice figure, and that's you are saying of this technical efficiency and technological gap and all. How we identify that the technology yield gap is coming due to efficiency, or efficiency yield gap is coming due to technology? because both are highly related. Suppose date of sowing is highly related with response of use nitrogen use efficiency or input use efficiency. Similarly, cropping system, soils, and fertility, and so. So how we know that it's a combined, or it's only we can see here only technology gap and then efficiency gap and then resource gap. But how we combine and look at technology as well as efficiency together to look, that's how can we impact yield, and then we can look in future.
Yeah. Well, thank you for this nice question. Well, if I understand correctly, just to summarize, then your question drives a bit more towards how can we have interactions between the different yield gaps, right?
Yeah.
Yeah, it's a good point. So I think, yeah, the step I take in this analysis is really static, and is really to say, okay, I have farmers, and I really want to disentangle different components. I really want to disentangle the interactions of these different activities. But of course, I mean, when we set up these these frontiers, for example, they all take into account all sorts of interactions between variables as much as possible, right? That you can acknowledge that, to at least the interactions between the practices that are used in farmers' fields, and that is basically this first frontier here. At least those are captured in explaining yield variability. I think that's a key point here. So when we look into the on-farm yields, then we take the observed amounts and then the interactions between those amounts to explain that variability. And then, okay, we can then disentangle further then, or this basic characterization of the technology used by the farmers. Now, the same can be done for the potential yield. I mean, as long as you have a crop model, I think we can run all sorts of combinations with different interactions actually between them to generate these sort of, future or optimal technologies. And I think, yeah, crop models are a great way to actually generate numbers in this regard, that you can just set up all sorts of combinations and of interactions that you like, of course, as long as the model accounts for them, to generate then outputs out of those. Now, I think really to link up efficiency gaps and technology gaps per se, I think I would discourage it, because I think that's that would be going a little bit against the philosophy, I think, with which we developed this framework. Now, what I've seen is that you can use these yield gaps, or the relative contribution of these yield gaps, to really characterize different production sites, right? Sites with high efficiency gaps, or sites with high technological gaps, or sites with both high efficiency and technology gaps. For that type of work, yes, that's possible to combine them. But now to really start looking into interactions between them, I would discourage that at least.
Thanks. We are already 10 past the hour. I will accommodate one last question if we have one last question. And then we'll close. If we don't have questions, we'll thank João again. I'm checking. Nobody wants to ask an additional question. It's good. Joe, I'm sure that you'll get many, many more questions when we'll have the chance to meet face-to-face or mask-to-mask. It depends. And I hope it's soon, sooner than later. So welcome again to CIMMYT, and thank you very much for your excellent seminar. It's a pleasure to have you with us now in CIMMYT and in the SIP program. Great. So good packing. I don't know when, but good move to Zimbabwe.
Good. Thank you very much, Bruno. And well, as you said, also I'm happy to any clarification questions that might remain. So just feel free to contact me. I mean, no problem at all with that. Also, is a good way to.
You have your CG mail already, no? You have your CG mail, but you don't have a computer yet.
Exactly, but at least the email is there. I think that's the starting point for communication, at least.
I heard that the computer is coming very soon, João. Sorry about that.
No, it's fine. Here is then the email.
Yeah. Okay. Bye all. Enjoy your weekend and safe weekend to all.
Good.
Bye.
Thank you very much, Bruno. Bye, everyone. Thank you for your attention.
Bye.
Bye.
Bye. Thank you.
Bye. Thank you very much.